Okay, this video is going to include both lessons 7 and 8. So let's start with lesson 7. It talks about the addition rule and complements. Our targets are I can use the addition rule to count, and then the second target I can use complements to solve probability problems. So we're taking a step back here to probability, which is what we started this unit with. All right, so let's talk about the addition rule. It says counting passwords with 3 or fewer letters. A computer password consists from 1 to 3 letters from the 26 in the alphabet with repetitions allowed. How many different passwords are possible? So we talked a little bit about this in the previous lesson, right? From 1 to 3 letters. So I think you can see we have separate cases. We have a case where you could have 1 letter, or you could have 2 letters, or you could have 3 letters. See how natural it is to use that or? These aren't all possibilities together, but they are separate cases that satisfy this. So 1 or 2 or 3. Well, if we have 1 letter and we have 26 choices, that's obviously just going to be 26. Or implies the addition rule, so we're adding. If we have 2 letters, 26 choices for the first spot, I can repeat, so 26 choices for the second spot. Or 3 letters could be 26 times 26 times 26. And you could use your calculator to figure that out. I'm not so worried about the final answer there. All right, so let's talk about something similar here with pins and how addition versus multiplication rule figures in here, and a little bit about complements. A pin is made from exactly 4 symbols. Notice here we can choose from the 26 letters and also the 10 digits. How many total pins are possible with repetition allowed? So between the 26 and the 10, we have a total of 36 choices, and we need a pin with 4 symbols. So I have 36 choices, but since I can repeat, I still have 36 for the other blanks. That is actually 1,679,616. If we repeat that problem, we've done this before, with no possible repetition, I now have repetition. I have 36 choices, then 35 choices, 34, and 33. That's 1,413,720 options. How many pins contain at least 1 repeated symbol? All right, well, if you look what we did up here, at least 1 repeated symbol. Here we had no repeated symbols, right? And this was all possible pins. So to find this out, we could take all possible pins minus those with no repetition. All right, so I would take the 1,679,616 and I could subtract the 1,413,720. That would only leave me 265,896. So sometimes you can more easily sort of use previous values to subtract rather than consider. Remember, if we were to consider at least 1 repeated symbol, we'd have to do 1 repeated, 2 repeated, 3 repeated, 4 repeated. We would have had to consider 4 cases. It's much faster to take all cases and subtract with no repetition. All right, so that's similar to what we've done in the past couple of lessons. If you randomly pick a pin, here we're back to probability, what is the probability that it contains at least 1 repeated symbol? So remember, in probability, I have to have the total number of possibilities right here, and on top I'd have to have the specific scenario I'm looking for, which is at least 1 repeated symbol. All right, well, those are all numbers I've calculated. At least 1 repeated symbol was the 265,896. The total possibilities, that was in part A, that's the 1,679,616. If I divide that out, I'm going to get kind of an ugly decimal. It comes out to be approximately 0.1583. So pretty close to 16% chance that you would get 1 repeated symbol. All right, so let's talk about this idea of complements. right? There are several marbles in a jar. You pick 2 marbles out of the jar. Suppose the probability of picking 2 marbles of different colors is 0.75. What is the probability of picking 2 marbles of the same color? Okay, that's where this idea of complements comes in. This is the exact opposite of what we're looking for. They represent completely separate, opposite cases. So I can do the probability of any pick, and I can subtract the probability of different colors, and that should get me the probability of the same color. Well, the probability of picking any 2 marbles, that's just 1, right? Like 100%. Absolutely going to happen. The probability of a different color, remember, was 0.75, so the exact opposite case must be 0.25. And if you think of it as percents, it might even be more obvious to you. I'm sorry, I'm off the paper here. You might say, well, it's a 100% chance that I pick any 2 marbles. If it's a 75% chance that I pick different colors, then it would be a 25% chance that I'd pick the same colors. Okay? So same idea down here in this last example using complements. There are 15 students in a classroom. Suppose the probability of having no repeated names is 0.85. What is the probability of having at least 1 repeated name? That should be the exact complement of no repeated names. So we should be able to take 1 minus 0.85, and the probability of at least 1 repeated name then would be 0.15. So the idea of a complement is there's no overlapping. This represents one set of cases, and then this would represent all of the other cases. All right, so if you could take the 2 cases, we could divide them up into those that are different colors and those that are the same color, and there would be no additional cases. It would just be those 2, it would just be these 2, and there's no overlapping. That's it for lesson 7. Let's go on to lesson 8, where we're going to kind of continue this discussion. Okay. Lesson 8 deals with Venn diagrams and overlapping sets. So some of this should sound a little familiar. It says I can shade the union, intersection, difference, and complement of a set. I know you've talked about union and intersection. I can solve problems with 2 overlapping sets, and then we're also going to work on one with 3 overlapping sets. So let's go over some basic vocabulary. Union, right, has the U symbol. If we want A union B, it means we want everything in both sets. So I would shade all of A and then include everything in B. So everything in either one of those sets, even the overlapping, all of that is included in A union B. Intersection's probably the more obvious one, right? Is an upside down U is the symbol. If we want A intersect B, we're talking about, of course, the overlap between A and B and just what A and B have in common. Difference, this might be something new in terms of Venn diagrams you haven't seen before. The difference, if we're talking about set B minus set A, so we're talking about everything in set B that's not in set A. Well, all these in here are also in set A, so I would have to remove all of those. So the only things that are in B and not in A, we could shade that section right there. Okay, all of those are just in B, not in A. Complement is what we were talking about on the last set of notes. Complement would be the exact opposite, where together they make the whole set. So the complement of A would be everything that is not A. So everything that is not A would look like this. And that's exactly what we were doing with the probability, right? If these represent the same marbles, then everything out here would represent different marbles. All right, if this was no repetition, this would represent at least 1 repetition. Together they make up everything, but we would shade if we want not A, that's the complement. All right, inclusion-exclusion rule. The addition rule only applies if the sets are mutually disjoint. They are apart with no overlap. So in other words, if I want to say everything that's in set A or B, right, I cannot just say that it's set A plus set B. If you look up at the diagram, I hope you can see why, right? if we draw kind of a picture here, let's redo it. Here's set A, and here is set B. So if I want A or B, well, let's think about A. Let's make A purple. And then B, if I make that red, hopefully you can see that there's a problem, because when I add up A and B together, hopefully you realize that this area got added twice. So I can only use this rule if these two don't overlap at all. Then that's true. The problem is when they overlap, we end up counting this region twice. So what we do is we subtract it once. So we subtract the intersection of AB. So let's say I subtract the purple one, then I would not include the purple one. I'd only have the red in here, and that would represent all of the objects. Okay, so again, we remove this because you can see by my colors, this part in here got counted twice. It got counted in with the purples, and this part also got counted in here with the reds. So we take one of them out. It gets a little more complicated when we talk about 3 sets. So let's go down here and let's try to draw the same picture to show you how this works. So let's make this set A, this set B, and this set C. So let's stick with the same colors here. There's A. I'm going to make B red. All right, you can already see we're counting some things too many times. And I'm going to make set C green. Okay, and let's see if I can kind of darken these lines in here. All right. So let's start out saying, well, what if we just added up everything that's in A, everything that's in B, and everything that's in C? I hope you can see that we're counting all this stuff way too many times, right? So if we use the model above, what if we get rid of everything? We counted this little football shape here. Well, we counted that twice. I counted it in the red and I counted it in the purple. So how about if I get rid of one of those? Just like above, I'll get rid of one of those intersections, either the purple or the red. I'll get rid of it. Let's ignore the middle just for a moment. Let's think about B and C, this little football shape right here, right? You can see here I've counted both red and green. So I've counted it twice. So let's say we get rid of one of those. We get rid of the intersection of one of the intersections of B and C because I've got that twice. And then if I look at this football shape right here, this is both purple and green. So I've counted it twice. So I'm going to get rid of one of the intersections of A and C. Now what gets weird is the middle here. Let's think about what we removed, right? Let's pick colors. So A intersect B. So let's say I got rid of purple here, right? So now there's no purple here in the middle from this first one. Then when I got rid of B and C, let's say I got rid of green, which means there's only red here. So now I'm getting rid of A and C, which means I get rid of it again. So now I've gotten rid of it too many times, right? So what I have to do is add back in an A intersect B intersect C, because what happens is when I remove this, I remove it, and I end up with nothing there in the middle. Okay, so by removing these footballs, I removed it here, right? That took one of the colors off. I removed it here. That took a second color off. And if I removed it here, that took a third color off. So that means all 3 of those colors got removed from that center section. So I'm not subtracting it. I'm sorry. I'm adding it back in. One more time. I'm removing these 3 footballs. This one, and this one, and this one. So from these outside sections, it's perfect because one of those colors got lifted. But the problem is here, there were 3 colors here in the middle. And each one of these took off one of the colors, so which means this got left blank. So what I do is I add it back in. Okay, so that's a little bit trickier. We remove the 3 crossovers, but then we have to add back in the middle because we took it out too many times. All right, let's see how this applies to some problems. So first case scenario is just with two sets. It says a school has 100 students that participate in the band or sports or both. So let's make a diagram. And we have band, and we have sports, and then we have this overlapping section right here, which would be that you participate in band and sports. That's the intersection. All right, so we know all of those numbers then should total up to 100. It says there are 50 in the band, so I know in this band circle, I've got 50. But it says of the 50 in the band, 10 are also in sports. So here's your intersection. We've got 10 that are in band and sports. So I'm going to put that here. But now it said there were 50 band. So if I'm just looking at this circle, and I've put 10 of them in the overlap section, and I have to have a total of 50, that means there are 40 in band who do not do sports. So together, 40 and 10 make up 50 band students. But it says there are a total of 100 students. I've only placed 50. It said that 100 do one or both of them. So that means the only chunk left is this sports without band, so that must be 50. The question says, how many total students are in sports? Don't answer 50, because remember, sports represents this whole circle. All right, so that whole circle represents 60 students. All right, it includes those that just do sports and those that do sports and band. Okay, let's take a look at this one, which gets a lot more complicated when we talk about three sets. Mr. Olson takes a survey in a large class to determine how many students speak a certain language. The finding is that out of 50 students in the class, 30 speak Gujarati, 18 speak Polish, 26 speak Spanish. 9 speak both Gujarati and Polish, 16 both Gujarati and Spanish, and 8 both Polish and Gujarati, or both Polish and Spanish rather. 47 speak at least one of the three languages. Now remember, there were 50 students in the class, and 47 speak at least one. All right, here's a special note. It says that when we write 30 students speak Gujarati, we mean that the total number of students who speak Gujarati is 30, and we allow for the possibility that some of those 30 students may speak one or both of the other languages. So in other words, this 9 that speak both Gujarati and Polish, that 9 is also included in this 30, just so you understand how the numbers are being presented. And the 8 that speak Polish and Spanish, the 8 that speak Polish are also in this Polish number. And the 8 that speak Polish and Spanish are also included in that Spanish number. Okay? So let's make a diagram. All right, and we've got Gujarati. We've got Polish. And we've got Spanish. So let's label those. All right. All right, let's think about that formula we had on the other page, right? We have, if we are Gujarati or Spanish or Polish, whoops, that would be Gujarati plus Spanish plus Polish. Now we're going to subtract those football shapes, so I'm going to subtract Gujarati intersect Polish. I'm going to subtract Gujarati intersect Spanish. I'm going to subtract Polish intersect Spanish. So I've removed the 3 footballs, but then I know this middle space got removed too many times, so I have to add back in Gujarati intersect Polish intersect Spanish. All right, so let's think about what we know, right? What's the total number of students that speak Gujarati or Spanish or Polish? I think we've got that down here. Don't we know that we have 47 that speak at least one of the 3 languages? So that will be on the left. All right. All the Gujarati speakers are 30. That includes everybody, even if they speak more than one language. We're going to subtract that out later. Spanish speakers were 26. Sorry, I put that out of order. Polish was 18. All right, now I'm subtracting those that I counted twice in Gujarati and Polish. So where is that number? Gujarati and Polish, there were 9. So I counted those kids twice. Now I also counted up Gujarati and Spanish, so those who speak both got counted twice. Gujarati and Spanish, that's 16, so I need to subtract that. And then here I counted up Polish and Spanish, so that means those who speak both got counted twice. That is 8. But now here's the key piece, right? By subtracting these 3 footballs, I've eliminated that middle piece, so now I have to add that back in. How many speak all Gujarati, Polish, and Spanish? Well, I don't know that number. That's the piece that's not given to us. So I'm going to call that X. So 47, if I compute this on my calculator, I get 41 plus X. So that means X equals 6. Once I get that number, I think I can fill in my chart. That 6 represents that middle intersection area. So that is this number right here. That is 6. All right. Now let's work our way out. Let's talk about what was the first one, Gujarati and Polish. That is this football right here. All right. So Gujarati and Polish, if we look up here, Gujarati and Polish was 9. Well, if I have 6 already in the football, that means I would need 3 right there. All right. Now let's do Gujarati and Spanish. Right? Gujarati and Spanish, that is this football right here, this horizontal one. Gujarati and Spanish was 16. Well, if I already have 6 in that football, I need 10 more to make that football 16. And now this football right here is the Spanish and the Polish. Spanish and Polish was 8. That would be in this whole football. If I already have 6 in that football, I need 2 more. Right? Okay, now let's look at this Gujarati circle. We know that we were supposed to have 30 Gujarati speakers. Well, how many do I already have in the Gujarati circle? I have 10 and 6 plus 3. 10 plus 6 plus 3 is 19. If I already have 19 in there, and there has to be a total of 30, 30 minus 19 leaves me with 11 just strictly Gujarati speakers. Okay? All right. Now let's look at the Polish. I'll make that one green. The total Polish number is supposed to be 18. Let's see how many we have in the Polish ring. We have 6 and 3 is 9, and 2 is 11. So if I take 18, which I'm supposed to have, and I already have 11 in there, that leaves me with 7 left in the Polish circle. All right, now this one, this purple one, represents all the Spanish speakers. The Spanish speakers are 26. All right, but I've already placed some of them. 10 plus 6 plus 2 is 18. So if I remove those 18, that means I only have 8 left who just speak Spanish. I think we can now answer all of these questions because we have all of our pieces. How many students speak none of the languages? Well, we had 47 who spoke at least one. Right? If you look back up, there were 50 students in the class, so there are 3 who are not represented. We could put that 3 outside the circles. We should have left that number. How many students speak all 3 languages? Well, that would be this middle number. That's the 6. That was what we computed. How many students speak or know Gujarati and Polish but not Spanish? So let's find Gujarati and Polish. That's this football. Right? But not Spanish would eliminate everything in the purple ring, so that would be 3. That is this number right here. How many students know Gujarati, but neither Polish nor Spanish? So Gujarati is my purple, but I don't want them to be in any of these overlaps because they can't be in the purple or the green. So the only ones that are strictly in the blue ring and nowhere else are 11. And then I've answered all my questions. That's it.